Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Kern Schools Federal Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, and the Kern High School District, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Hey, we're here with a little math in the real world, one of my favorite parts of the show. We want to know how math works all around us. And what better place to come here than to the Buena Vista Museum of Natural History, and here in Bakersfield, just right down the street from our studio, we have our good friend, Dave Hanley. So lucky to have you again. We always love to chat with you. We've been talking a little bit before we got on air about the math that goes behind the science. Right. So I thought maybe we'd talk just a little bit about integral equations because they have to do with movement of things. So, you know, students have always, they know how this works, right? They get a coin, they spin it around, there goes the coin, and it goes down pretty quickly, and you can do all kinds of little fun elementary games, and you try to stop it in mid.
I love a quarter for every student that tried to do that to make me nuts while I'm trying to do a lecture, right? You know,
a little bit tough in the classroom, but everyone can kind of relate to that. There has to be a way to describe that momentum and the fact that it goes down quickly or not so quickly. But you have something here that you can kind of show us maybe. This one doesn't go down as quickly because it's a heavier disc.
Well, somebody made it, yeah. Now we're talking about integral equations, and the whole concept of integral equations is they're not linear.
Right.
In other words, so when we're talking about the sharks and we're talking about the other things, we'll talk about things that do not have a linear relationship with their growth or expansion, that sort of thing. It goes growth or diminishing. So in the case of this is an integral equation. We're talking about a disc. We're talking about this metal disc, very smooth, lowering the friction. This has the ridges on it. The desktop is pretty cool, but it does have more friction. There's more friction involved, so it takes a little bit longer for it to spin. This is a brushed steel. This is a glass, smooth metal mirror, concave to keep it in the center. And so this was manufactured to be able to do this demonstration. And it's called Euler's disc because there's a formula at which this is falling at an ever diminishing rate. It starts out with a greater fall, and it cuts its distance as it falls to less and less and less. Right. It would go on for infinity and never slip down if it were not for gravity. Right. So gravity is cutting into the momentum. Okay. And so Euler figured out the formula to determine at which point the momentum would become overcome by the gravity. Okay, gotcha. And so that's why it's called Euler's disc. He's got the formula. It's on the back of the box.
Sure. Now we can see this going down and down and down, but we have a different effect that we can do if we can only see pieces of it, and you do that with a strobe light, right?
Correct.
Okay.
Okay, so we'll do the light. We'll do the strobe light. Come on. Right. There we go.
And from my perspective, it looks like that thing is completely stopped. It really is a unique look to it, and it's just taking little individual images of that thing spinning, but it's taking an image of it in almost the same place each time it goes down.
And now the rate of fall. Well, the rate of fall is changing. Sure. And it is. So this is what we use to time our engines. Right. So this strobe effect, this is the strobe effect of the sun. If you're driving down the freeway, the strobe effect. So we're getting two for the price of one. Sure. We're getting the effective strobe, and we're also getting the effective integral equation. And the fact that it does look like it's changing its action is because it is falling at an integral rate. So it did stand still for a moment, but then it changed because the rate is constantly changing. Yeah. And now gravity is about to overcome our momentum, and it's a... Come on, slap
there
down.
It is.
There we go. All right.
So we finally get to a flat disc there, and that's going to happen just because we have some things in this world that we can't completely describe with mathematics. But the main function of this, or the main part of...
The point is, that was Euler. Euler described how we take gravity, the formula for gravity, added into a typical integral equation, which is the rate of diminishing fall, not linear, but diminishing okay?
Right.
Integral, diminishing. And so he added in the factor of gravity and made it an equation where you could anticipate exactly how long with given momentum it would take before that would fall and hit.
Right.
Then I discovered, to my pleasure and amazement, the thing about neodymium magnets in an aquarium.
Sure.
And of course, the formula would fit exactly for that, for those to come to a standstill in reverse instead of down, up. But we would have to add in the force of the magnetism instead of gravity.
And that rate would change up or down depending on how many magnets you had and how wide you started the initial spin and all those factors, of which we can control in our equation if we had an integral equation, right?
Correct.
Yeah.
The patterns of science
Yeah.
in the natural world.
The power of math, unbelievable. What we really want to know is where this happens in the animal world. So when we come back, we're going to look a little bit in the museum, talk a little bit about sharks and how integral equations end up being part of their growth and development.
Non-linear growth and mass development and megalodon.
There you go. We're back with some math in the real world, and this is our world this afternoon. We're here with Dave Hanley, and Dave, we know, if we've been in Kern County at all, that there are a lot of shark's teeth around this place. There's a place called Shark's Tooth Hill. I know that it's been part of my experience as a camper and all that fun stuff, and we were talking earlier about integral equations. So let's put those two things together. We have a big fossil bed here in Kern County, and we have integral equations that can describe certain things, growth patterns in nature, right?
Right. We have the largest Miocene fossil bed in the world here in Kern County. And the Miocene, 12 to 17 million years ago, is 5 million years.
Okay.
And it's going to be one of the summative things that we're going to do too.
All
It's about the
right.
teeth that are in the Shark Tooth Hill Formation.
Okay.
It's called the Shark Tooth Hill Formation because of the teeth, because shark's teeth are Rolodex. And some of us older people know what Rolodex is. A lot of the younger people don't know, but that's where you have all the cards and they keep rolling forward. Mm-hmm. And so the teeth keep rolling forward. The shark may lose as many as 1,000 teeth per year. Wow. And when you consider that we were here for 1 million years, at any point in time there was 1 million sharks in the water, and 1,000 teeth per year for 5 million years with a million sharks. There's a whole bunch of teeth down there in the largest Miocene fossil bed in the world. Okay. It happened to be at the time of the megalodon shark. Yeah. So when I tell people that we have the largest Miocene fossil bed in the world in Kern County, that's ours. They come from Germany and Japan to see our fossils. Right. And so this guy was around then, he was popular then. They want to find out about megalodon, they come to Kern County because we've got the best examples to show them.
Sure.
Okay, so here's the megalodon shark. He got up to 60 feet long. Imagine the really big school buses. Right. Put a 6 foot by 6 foot jaw on the front of that bus, and it gives you an idea how big that shark was. Right. He was a huge predator. That was a giant predator. They snacked on baleen whales. They snacked on adolescent baleen whales. They snacked on alodesmus sea lions, like elephant seal-sized sea lions. Oh, wow. Now, let's not mess around with little seals. Those things are little. So anyhow, it's the same relationship. You know, again, we're talking about non-linear growth patterns. Okay, so I had Burmese pythons hatched out in my classroom. Okay, they hatched out at 18 inches. At 18 inches, they were approximately 8 ounces. Okay. By the time they were now twice that, which would have been 3 foot, now all of a sudden they're like 5 pounds. Oh. So the growth rate is not linear. It's an integral equation. It's a logarithmic growth pattern. Okay. And so now we talk about megalodon shark, and they were live bearers because they had internal fertilization. The mother would be able to keep the babies on board, didn't have to dump a whole bunch of eggs down. The mothers would be able to have the baby inside.
And this is the representation of a live
This would have been the
shark
the size
at birth.
of newborn at birth megalodon shark. It would have been about 6 foot long, weigh about 200 pounds.
Wow.
Now, at 12 feet, we're talking about 1,000 pounds. We're not talking about
so
400
double in
pounds.
size, but definitely more weight.
Way more, 2.5 times.
Yeah.
Okay, so we're talking about integral equations. We're talking about logarithmic growth. We're talking about non-linear growth patterns, and that's typical of snakes, that's typical of sharks, that's typical of whales, that's typical of, just everything in the living natural world.
Sure. Wow. Now, do the teeth growth, you were talking about the Rolodex part, does that have any kind of integral relationship at all about how fast they grow or how fast they're gone, or is it matter
I
what they
understand
eat?
we might be doing another segment in a little bit about a summative relationships. And so this becomes a summative relationship because if we're talking about 5 million years,
Right.
at any point in time, 1 million sharks
Sure.
losing 1,000 teeth per year because of the Rolodex teeth, they're constantly moving
They
forward.
just keep on generating.
This tooth was one of 3 we found in the skull of a baleen, adolescent baleen whale that we were excavating.
So that's how you know they ate those.
Well, they come off as they eat.
Sure.
And so they don't die to leave their teeth behind. A whale dies to leave a tooth behind.
Okay.
A sea lion dies to leave a tooth behind because they're mammals.
Sure.
But sharks, they don't die to leave it behind. That's why it's called the shark tooth hill formation.
Mm-hmm.
So look at the summative equation. You want to figure a number that you can't calculate, you probably can't even describe.
Right.
It requires a thing that we use called summative equations.
Okay, gotcha. So we have a lot more math to do. Wow, it's so exciting. I love to see the fact that we can see the math going on in the natural world, and I love to have you explain that to us. So really, really appreciate that.
Science
Yeah.
is not about knowing. Science is about discovering the patterns in the universe.
Right.
And the best universal language for that just happens to be mathematics.
Ah, such a shame. Well, heck, let's make a show about it. Oh, we have a show about it. All right. I know you couldn't wait to come back to the Buena Vista Museum of Natural History here in Bakersfield. We have some math going on in the real world all around us, and Dave Hanley is going to show us a little bit more about integral equations. What a wonderful way to explain to students how we can make things increase, but then not increase at the same rate. The rate changes. So tell us a little bit about this experiment that you show your students, which I think is a wonderful way to show that relationship.
Okay, so absolutely, this was one's kind of fun. I like candles. I like burning things. Students like burning things.
Right,
Anything
yeah,
burning
it
is
catches
always
their
fun.
eye.
And so if you notice in here, we have actual one real candle, and this is an optical illusion sort of thing.
Right.
And so we see that we have visually we see at least 4 candles.
4 candles.
Now I'm sitting here playing with the idea, since it now has a flame on it, I actually see 7 flames.
Oh, interesting.
But that's just an added little thing, just for
Right.
the sake of complexity. And,
Right.
and
But if we're looking at it from this angle here, we can see 4, 3 in the mirrors, and 1 real one right in front of us, right?
Right.
Okay,
I
so let's-
had to add that. I'm sorry.
That's all right.
That's mean. Okay, so now I'm going to change the angle in here. This is a 90-degree angle. I'm going to change the angle by about 24 degrees.
Okay.
So I'm going to change it by about
So
12
now
on
the
each
walls
side.
are closing in.
So we got a change of about 12 on each side, which adds up to a total of 24.
And
And-
now we seem to see more candles.
See 5 candles?
5 candles, yeah.
Okay. I'm not writing lines to see, but I'm trusting you.
Yeah,
Okay.
I see
Now,
5. There you
now
go.
I'm going to change each of the wings by 6, which is half of the original change. So I'm going
Right.
to change this by about 6 degrees.
Right.
And now I think we're going to have way more candles.
Yeah, that's right. I
Okay.
can see 6 at this point.
And
yeah.
so now if I change it by 3 degrees on each, then we'll change it even more. So you see what we're doing is we're describing the purpose of science and mathematics is to describe the patterns in the universe.
Right.
And so this is we now have a relationship between the changes in the angles.
Right.
And it's in geometry, but it's still an integral equation, so
Right.
it's still algebra, but it's still geometry, but
That's
it's
right,
still...
'cause we
it's
can't
all-
describe that
Oh,
with
it's
a
all
linear
just mathematics. I'm a non-denominational science mathematician.
That's a wonderful example of a way to show that we have a relationship, a direct relationship, but it's not linear. So I like that one a lot. Now here's one that I think is the most amazing. We talked a little bit about amino acids and how they come together to make proteins in our bodies, right? But we have some proteins that have two or 3 or 4 amino acids, and some that have a whole lot more than that. Tell us a little bit about
Okay.
the building blocks.
We're
of
really
proteins.
proud of ourselves as humans. We're Homo sapiens, which means in Greek, human ideal, and we ain't close. I'm
Okay,
sorry.
all right.
But here's what we've done. We've done computers.
Right.
We're really great because we've done computers.
Sure.
Nature has this computer way beat. We got us
okay.
totally beat on a computer.
Yeah.
We started out with a computer program.
Right.
Where with our computer programming, we started with binary. Okay.
Yeah.
So we go nine in a row. So what is a bit, a byte, whatever, 9 in a row. And so 1, that's 1. This is 2.
Right.
This is 3, and so forth.
And so each of these places either on or off.
right,
And
exactly.
so if you're trying to get some information through, This would be a long way to do it. You could do it, but it would be a long way to do it.
They had
Take a
whole
while.
rooms. Well, now they do it with the little silicon things, and they positively or negatively charge the silicon things on and off. Now they can do null, positive, or negative, and now they're up to a train area, and that's really choice. But nature.
Nature's better at this. All right, tell us what we're going to do here.
So what Mama Nature has done is she's done all the processes and stuff that we want to do with computers, only with living things, and she's done it with proteins and amino acids.
Right.
Okay. Proteins are defined as 2 or more amino acids joined together.
Right.
And all of those proteins do all of the functions of all of the living world.
Okay.
And so that's what we do with computers. We do functions with computers. We do functions with living things. And so that's what Mama Nature does. So here's what Mama Nature's done. She says 2 or more amino acids. Now there's 20 amino acids. So we have over here, we have the chart. I've got this over here. I did a quick little add up of it. So that in the chart here, we've got 20 of these are the stop codons. So they tell you when to stop making a protein. So they don't count, but all the rest of these 20 are all proteins. They're on this chart, or amino acids, and they're on this chart, and triplet coding in the DNA transferred to the RNA gives us the amino acids that are joined each time in each of those steps.
Okay.
So now, if we go back over here, we understand that there's a protein in our arm, a fibril protein in our arm that takes 1,332 amino acids.
Wow, that's where this number comes from.
So
And you
this
said
is-
that it has to have at least 2.
It has to have at
somewhere
least
between
2.
2 and 1,332. We're in there somewhere.
That's in there. So the way we figure out how many possible proteins there are in the living world is these are the building blocks. These are the processes. So we got a few processes we get to do.
Sure.
We start with 2 to the 20th power because that's the number of proteins we can make with 20 amino acids. 2 to the 20th power is how many proteins with 2 amino acids.
Sure.
Then we get to add that to 3 amino acids to the 20th power. Then we add that to 4 amino acids to the 20th power, and 5, and so forth until we get down to 1,332 to the 20th power. And one of my students says he did it right. I'm not sure whether he did it altogether correctly, but he tried doing the summative on this, and he came up with 8.65 times 10 to the 76th power. That would be 8 with 76 zeros behind it, or
Right.
74 zeros with 6, 5, 7, and
Sure.
74 more zeros behind
Just a small number in
it.
nature.
I don't know how to name it.
We don't even know what to call this number. That's right. So Mother Nature has done math way before we thought we could understand it all.
Computing.
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 Right. Yeah.
This is the computer we want to build.
Right. Yeah, that's it. Boy, and be able to do something, crunch the numbers like that, it'd take a little longer than recess to make sure you have all those numbers, right? There you go. We're so grateful to have been able to speak with you today. We're so always amazed to see all the math that's around us, and what a better place to be than here at the museum. Thank you for your time.
Oh, my pleasure. Thank you. It's a pleasure. I love
Yep.
it down here. This is what we're about.
That's it. That's it. So come on down to the museum if you want to see a little bit more about math in the real world, a little bit math in the natural world.